Okay, this is a walkthrough of a conservation of mechanical energy problem where gravitational potential energy is going to change. So this is whenever the height of an object is changing, you have to use the gravitational potential energy. Okay, so let's say that we have a ramp and we don't have to know what the shape of the ramp is. That doesn't change anything. And let's say that at the top of the ramp, we have a cart. And it is moving at the top of the ramp 2 meters per second. And the ramp has a height of 0.5 meter. And we want to know what's the speed of the cart at the bottom of the ramp. Okay. Well, the first thing you have to do is make sure that this has that this problem, you can use conservation of mechanical energy for it. So what that means is that the forces that are applied to this body during this motion work for conservation of mechanical energy. Remember, in this class, the simplest way to think of that is here are the forces that we can deal with. Gravity, spring forces, these are the conservative forces, so these are the ones that we have to deal with potential energy. And then there are also two non-conservative forces we can deal with because they do zero work. That's normal forces in rolling and sliding. And centripetal forces in circular motion. So unlike these first two, these are non-conservative forces. But they do zero work. Okay, so let's think of a free body diagram of this thing while it's rolling down the ramp. There'd be a weight force acting down. There'd be a normal force pushing up, and that's all that's acting. And so we can see this one is fine. We can represent that with potential energy. And this one is fine because it doesn't do any work. Okay, the next thing we have to do is write out in two columns. We're going to have an instant 1 and an instant 2, and we're going to calculate the potential and kinetic energy at each of those two instants. Our first instant is going to be at the top of the ramp, and our instant 2 is going to be at the bottom of the ramp. So instant 1 is at the top, and instant 2 is at the bottom. Well, since the only conservative force we have is gravity, is the weight, we're only going to have potential energy due to weight. When we have potential energy due to weight, we always have to choose a height that we're calling zero height. And it doesn't matter what height you choose, but you have to be consistent with it. So let's choose our height equals 0 to be at the bottom of the ramp. Okay, so now pause the video for a second and see if you can fill out this table. All right, for instant 1, our potential energy, our gravitational potential energy, is going to be the mass. We don't know what that is. Times g, which is 9.81 meters per second squared, times the height. Since our h equals 0 is at the bottom of the ramp, the height at the top of the ramp is 0.5. And so this gravitational potential energy at the top of the ramp is equal to 4.905 m. And now the kinetic energy at the top of the ramp is 1/2 times the mass times the speed squared. The speed is 2 meters per second, so 2 squared. And so this comes out to be 2m. Now at the bottom of the ramp, our gravitational potential energy is the mass again, times 9.81 again, times the height, but at the bottom of the ramp, the height is 0, so this all comes out to be 0. And finally, the speed at the bottom of the ramp is going to be 1/2 times the mass times the speed squared. That capital V is the speed at the bottom. So we can just write this as 1/2 mv squared. Now that we have this, we can add up the potential and kinetic energy at instant 1 and set it equal to the sum of the potential and kinetic energy at instant 2. And so what happens when we do that? So 4.905 m plus 2m is equal to 0 plus 1/2 mv squared. Now pause the video and see if you can use this equation to solve for v. Okay, the first thing you have to notice is that you can divide m from both sides. So all the m's go away, and what that says is that the mass of this thing doesn't matter. Which is good, because I didn't tell you what the mass is. It could be 50 kilograms, half a kilogram, whatever. The answer would be the same to this problem. And so we have 6.905 is equal to 1/2 v squared. Multiply both sides by 2. And you get that v squared is equal to 13.81. Now take the square root of both sides, and you get plus or minus 3.72 meters per second. We're looking for a speed, and speeds are always positive, so I'll take the positive one of these. Okay, so what that says is if this is moving 2 meters per second at the top of this 1/2 meter high ramp, and it rolls down the ramp, when it gets to the bottom, it will have sped up to 3.72 meters per second.